So I'd like to talk a little bit more about the MIRI instruments design and conception in terms of the science goals, and particularly in terms of carbon. The community that we're representing today is sort of nano space for measuring signatures, for example, of pHs.
Mm-hmm.
Can you maybe tell us a little bit about how that was designed and what were the sort of science goals that were being aimed?
Okay, so Webb, as a telescope, it was conceived back in the 90s as the follow-up to the Hubble Space Telescope. So there was an awful lot of emphasis on imaging. But also imaging of the high redshift universe. So for cosmology, so the deep fields that were measured by Hubble back in the 80s and 90s, the idea was to build on those. Going into the infrared, because of course, you're going further with redshift, more distant objects, and so that you're looking closer to the origins of the universe and the early galaxies, early stars, that sort of thing. So for the PAHs in particular, where that really came from is that the telescope was seen as needing to do more than just straight imaging, because it was a big technical endeavour. I mean, people will be aware the cost overall in the end is some 10 billion money units, but it's dollars or euros or whatever. But and so it needed to serve the wider astronomy community than just the crazy cosmologists. And so and it's a good thing that was the case, really. So in the case of MIRI, the instrument selection was kind of important. There are 4 instruments on Webb. 3 of them operate at so-called near-infrared wavelengths. 1 only was MIRI, and that operates from wavelengths from 5 to 26, 27 microns, something like that. Because it's the only instrument on board that works at those wavelengths, we had to give it all of the capabilities that an astronomer might want to have. And so rather than just imaging those, having a narrowband filter which will pick out each of those pH features in turn, I think the key kind of breakthrough operating configuration of MIRI is the spectroscopy. So we have an integral field spectrometer, which has a field of, it varies, but it's roughly 5 by 5 arc seconds. Smaller at short wavelengths, a bit longer at long wavelengths, but 5 by 5 arc seconds. So that matches well to circumstellar disks, interacting galaxies. And this instrument, the MIRI medium resolution spectrometer, it can measure the spectrum at every point in that field simultaneously, so it's very efficient. So you get spatial and spectral information simultaneously. Now the other parameter that you can change or set with the design is the spectral resolution. So the resolving power of 3000, that gives you can resolve, you can characterize the width of a line by the velocities at which the gas or whatever it is that's emitting that line are moving at. And so that 3000 is matched to about 100 kilometers per second line widths, which is the sort of thing you see in a galaxy or in a, well, it's a bit fast for a stellar outflow, but it's in the right ballpark, okay? And so it's the spectrometer, the imaging spectrometer that has had, in the first couple of years of operation at least, that's produced some quite spectacular, spatially resolved spectra at this reasonably high resolution of, as I say, disks and galaxies, which show these bright polycyclic, PAH features, so the carbon, carbon molecules that you're talking about, and but superimposed on those the fine structure lines from these ionized species as well. So in one shot, you get you can look at how the excitation varies with distance from, let's say, the central black hole in an active galactic nuclei or the central star in a circumstellar disk. Yeah. And not only do you get the ionized species in their fine structure lines, but you'll get molecular lines from CO2, CO, hydrogen lines as well. So it's in one shot you're getting a kind of a a chemical breakdown and physical breakdown of an object in one go. And so, yeah, that's really been the power. And it was kind of, as I say, that's really wasn't the main focus of the observatory from day one, mm-hmm. but that's turned out to be really one of its strengths, I should say. And the quality of those spectra, I found, as an instrumental sort of person, they remind me very much of lab quality spectra that you take of a gas sample, but this is of an exoplanet that's tens or 100 light years away, and so the amount of information that sits in there, and that would be of particular relevance for the organics that are, in this case, emitting in the atmosphere at around. Absorbing in the exoplanet atmosphere at wavelengths between 5 and 10 microns. You can see that there's an awful lot of high signal-to-noise data in there that so far the retrieval experts haven't really got to grips with. So it's...
Yeah, that's a complicated spectral region to deconvolve.
Yes.
The signatures.
Yeah. So there's plenty of... It'll keep people occupied for a long time, I hope. Yeah.
Definitely, yes. The archive is already getting filled up. The spectroscopy has been with MIRI, when the raw data comes in 12 little segments of spectrum that need to be stitched together. The reconstruction of the date of the spectral cube, which is it's spatial information in 2 dimensions, and then the 3rd dimension is wavelength. Being able to do that accurately was dependent on a huge. Actually, I'd say it was an awful lot of work that went on during commissioning and post-commissioning by the people at Space Telescope, but also by the MIRI commissioning team, to get that process calibrated and working properly. Because it's very easy to put spurious artifacts in your data, which, if you're not really careful, could be interpreted as being real features of the astronomical target. So, are you? I think you said you were involved in some GTO projects. Are you intending to keep being involved scientifically?
For me, to be honest, my real love is in building the instruments, and so I've moved on to the ELT METIS instrument. So it's another. But that's a subject of another discussion, probably. Not quite so great for PAHs, I've got to say. I mean, we're looking at resolving powers of spectral resolutions of 100,000, spatial scales now of down at 20 milliarc seconds per pixel. It's the next step forward.